Adam Berrones today. Just a little background on Adam. Adam started out here as an undergrad in the Kinesiology department, graduated here. Then he matriculated into Florida Atlantic University, spent there a couple years as his master's. Then after that, Adam took some time off, experienced the real world, and then decided he wanted to come back and do his PhD. So that brings him back here to UK. And Adam's been working with me, and he's now in the second year of his PhD program. And now he's beginning to think of ideas of research projects. And so this is one of Adam's ideas that he's going to discuss today. So without further ado.
I appreciate it. It's an absolute pleasure to be here speaking with you. So thank you very much for your time. I'm appreciative of Dr. Clacy for having me. And I got to tell you, when I walk around these hallways and I see my face on the flyers, it's almost like I don't even recognize that guy. It's like I'm here to see Adam's presentation because I look at it and it just seems like a different photo. When I thought about starting his presentation off, I couldn't think of a better way to do that other than to thank people who have gotten me here. So I'm appreciative of my advisory committee first and foremost. That includes Drs. Brad Fleener, co-chair Dr. Mark Abel, as well as Dr. Lance Bollinger, Bernard Hennig, and Kevin Pearson. So to them, I'm extremely thankful. I'm appreciative of being a mentee of them, and I'm also appreciative of anybody who works in Fleener Lab. We do phenomenal research, experimental research, go on trips, present some articles, and it's, again, something that I enjoy doing, so I appreciate you listening to me today. I have no conflicts of interest to disclose. A brief outline. Today I'm going to be talking about obesity. We're going to look at obesity. We're going to talk about the prevalence of obesity. We're going to see that obesity increases inflammation. I'm going to show you a couple slides to present that framework. Then I'm going to show that the inflammation increase as a result of obesity drives cardiovascular risk. One exemplary disease of cardiovascular risk is arteriosclerosis. So I'm going to say that obesity drives inflammation, which increases cardiovascular risk, particularly arteriosclerosis. I'm going to look at the energy balance equation. I'm going to see, well, this oversimplification of what happens regarding energy coming into the body, energy leaving the body, how does that relate to obesity and what the phenotype of arteriosclerosis looks like. We'll look at reducing the calorie content of foods, in particular the carbohydrate. Then we're going to look at this molecule derived from Stevia rebaudiana that I think is very interesting and very worthwhile. We're going to look at its chemistry, we'll look at extraction, we'll look at sensory properties, we'll look at a few practical applications of this molecule. I'm going to take Stevia rebaudiana and I'm going to bridge them between arteriosclerosis and obesity as an anti-inflammatory agent. So I'm interested in this as a functional food to modulate obesity, and I'll present the data to you today. And one potential mechanism I'll show you is decreasing NF-kappa B signaling. So this is going to be what I talk about today. I think an important way to start off the presentation is to look at a heat map, and this is a 2010 CDC map of obesity. And you can see that the obesity is omnipresent. While it is concentrated in the south, states in the west and the north, we're talking minimal rates of 20–24% obesity. It's an epidemic. I ask questions to myself all the time. Questions about biotechnology, questions about obesity epidemics, questions about whatever. I'm not afraid to tackle any subject matter. One question that I constantly arise to is, will obesity increase or will it decrease? And you look at the trends, since 1980, 75% increase in obesity. And that's since 1980. You got a third of adults who are obese and a sixth of children. This could be the real problem here, is that the children who learn behaviors will take those behaviors into adulthood, and then they'll be adult obese individuals, having learned the skills to become a proficient at obesity as a child. That's the real scary portion. If I had to answer my own question here, I would liken the United States to a barcode. And if I scan that barcode to answer my own question, I would say it's going to accelerate, and it's going to accelerate very fast. Obesity drives inflammation. As you can see by this simple cartoon, healthy adipose tissue has lower amounts of macrophages. When you have increased adipocyte swelling, you will increase macrophage infiltration. This excessive weight gain leads to adipocyte swelling. Now, it makes sense that the fat cell will accumulate substrate. And the problem with this is that we eat too much substrate. We got all these food stuffs coming into our body. Healthy adipose tissue becomes excessively hypertrophied in obesity, and this is to accommodate the substrate. You will increase triglycerol storage, and this is a normal process. But obesity is characterized by a low-grade inflammation. This is a chronic state, and I'm going to present to you that data. The problem with obesity is that the rapid fat accumulation outpaces angiogenesis. And because of this rapid expansion of the adipocyte, blood flow can't keep up to the metabolic demands of the fat cell. And when this results, hypoxia is going to signal a whole bunch of factors, particularly chemokines that will attract macrophage infiltration. Macrophages will secrete a variety of adipokines that attract other types of immune cells and will promote a manifestation of low-grade inflammation. When you look at lean adipose, it's different than adipose that's very obese. The phenotype is different, and this slide orients you in that perspective. Lean adipose tissue is an anti-inflammatory phenotype. It's small. The relationship between the immune cells and the adipocytes include adipokines that are anti-inflammatory in nature, and we're talking about interleukin 4, 10, and 13. Those cytokines are going to promote signaling that are different than adipocytes that are swollen, hypertrophied, and remodeled, as you see in obesity. These adipokines, interleukin 4, 10, and 13, which polarize macrophages to the M2 subtype, will be responsible for tissue repair, wound repair, and healing. This is a balance in the body that's constantly changing. There's an anti-inflammatory, pro-inflammatory balance at any one time. And the idea is that we want to increase the anti-inflammatory capacity of the adipocyte and the immune system and reduce pro-inflammatory expression. Adipokines like interleukin 4, 10, and 13 will promote cardiovascular eufunction. This again is an anti-inflammatory enhancement. This is ideal, this is positive, this is minimizing cellular stress. This will favorable nitric oxide production and then therefore bioavailability. This increase in bioavailability will promote vasodilation and enhance endothelial function. Now this is in lean adipose tissue. Not all adipose tissue is created equally. It will vary from depot to depot, and then within the depot, certain microenvironments will have different levels of cytokines present. So it's a highly specific, highly regulated microenvironment that we're talking about. When you look at obese adipose tissue, increased substrate, promoting triglycerol storage, adipocyte remodeling, expansion of the cell. What happens is you see a pro-inflammatory phenotype. The interaction with the immune cell, the immune system, is going to promote a different function. The adipocyte, because it's hypoxic, will be more likely to be apoptotic. And because of this, you will have macrophage infiltration to clean up cellular debris. And it will create crown-like structures that can be seen with staining, in particular perileptin. The adipokines, it's a different set of regulators. The molecules are not the same in obese adipose tissue as they are in lean adipose tissue. We're working with a different set of cytokines. These cytokines, including interleukin 1, interleukin 6, TNF-alpha, interferon gamma, they're going to signal different types of immunological responses. They're going to increase the temperature centers in the brain. They're going to increase swelling, extravasation of leukocytes into the tissues. Interleukin 6 will stimulate the liver to promote acute phase protein production. Negative acute phase proteins such as albumin will decrease during inflammation, whereas interleukin signaled, again in the obese adipocyte, will signal the liver to promote acute phase proteins that are positive. And I'm talking about opsonins, coagulation factors. I'm talking about C-reactive protein, serum amyloid A. These proteins secreted by the liver in response to these adipokines will promote inflammation. C-reactive protein is an example of that. The phenotype in obesity will be cardiovascular dysfunction. As a result of M1 macrophage polarization, the difference being, it's a macrophage. On one end of the spectrum, you got M1s, on the other end, you got M2s. M2s can be broken down into subsets A, B, C, so on and so forth. An M1 macrophage is like, I was trying to think of an analogy to describe this. It's like a soldier on the battlefield doing dirty work. An M2 macrophage is like a nurse cleaning up the wounds. They do the dirty work. There's dirty work to be done in an inflamed adipocyte because the cell becomes apoptotic. And we're talking about a different set of players, which will increase pro-inflammatory state, will promote endothelial dysfunction as a result of decreased nitric oxide bioavailability, promote hypertension, and atherosclerosis. Now this ratio that I keep mentioning between the M1s and the M2s, or the classically activated and alternatively activated macrophages, in humans, the research is coming. In animals and experimental models, they have shown that in a normal mouse, the M2 to M1 ratio is 4:1. Anti-inflammatory 4, pro-inflammatory 1. However, when you induce obesity in a mouse, what they've shown is that the M2 to M1 ratio changes. You see a reduction in anti-inflammatory phenotype in the adipocyte that is increasingly swollen. That's an important distinction of inflammation driving cardiovascular disease. So I'm now linking arteriosclerosis, which is a vascular aging problem. The vascular system becomes calcified and rigid. Those pro-inflammatory adipokines that I just were talking about are secreted by adipose tissue. There are different depots of adipose tissue in the body. One depot of interest is the perivascular adipose, PVAD. Peri stands for around the vessel fat. Now when you look at an artery in a book and you see it in a presentation in class, this is how they typically present arteries. And here's the aorta. It looks clean, it's delineated, it's very easy to interpret that that's a pipe that, through which blood will flow. But what you should really think about the artery looking like, if we're looking at a cartoon still, is this. And what this shows is a bunch of yellow fatty substance around the artery, which is how the artery really sits in vivo. Arteries are almost every artery in the body, with the exception of a few beds in the cerebral vasculature and a few beds in the mesentery. Every single artery is surrounded by fat. And this fat, called PVAT, secretes those pro-inflammatory cytokines that I was just mentioning. And that relationship has been explored. There was a brilliant paper just last year talking about potential mechanisms of arteriosclerosis, which is my disease in question regarding cardiovascular system as it relates to obesity. And some sources of this include the arteriosclerosis, which is vascular hardening, decrease in bioavailability, increase in oxidative stress, calcification, extracellular matrix remodeling, and increase in vascular smooth muscle tone. Arteriosclerosis is a disease that is accelerated by obesity. And the reason, in part, is because the inflamed PVAT will release adipokines and will communicate with the local vasculature, and in my representation, the aorta is the artery that you don't want to be interfering with. Feel free to ask any questions anytime. You don't have to wait till the end. If something pops up, you're not sure, you want more clarification, if anything comes in your brain, let's share it. I'm open. Let me take a break for a second.
Is that, excuse me, perivascular fat, is that eating an American diet or is that eating a?
So when you say,
So if you take a population that has what we would consider a healthy diet, do they have less perivascular, or is that just?
yes.
Okay.
Yeah, that fat depot will increase and decrease with weight gain. So yes, populations who eat foods that promote obesity, the PVAT storage site will increase, and those pro-inflammatory cytokines will promote, I'm suggesting, arteriosclerosis. Okay, let's look at our schematic here. Got a nice little image here representing a P wave, a pressure wave. This pressure wave is this is a schematic what the left ventricle does. The left ventricle generates the incident pressure wave. You can feel the pressure wave. We all are familiar with the pressure waves. You can feel the pressure wave at the carotid, radial, brachial, femoral. You can feel the pressure wave. When you feel your pulse, that's the pressure wave that you're feeling. Because you can feel the pulse at more than one site, at more than one time, we can derive a few interesting derivatives of that. Namely, this pulse wave velocity. So how we determine arteriosclerosis is by the pulse wave velocity. We look at the velocity of this pressure wave as it's created in the left ventricle and as it travels through the vasculature. We can do this by measuring two known points, the carotid and femoral arteries. We'll take the superficial distance between those 2 points, which will serve as our distance component. We'll take the time differential between the R wave and the beginning of the foot wave of each of those two pulse locations. That will serve as our time component. And we can calculate a velocity of the pressure wave as it travels through the vascular tree. Pulse wave velocity does not equal blood flow velocity. It's a common misconception. This is what I'm referring to by this schematic and the measure of arteriosclerosis is the velocity of the pressure wave, not the velocity of the bulk flow fluid. They're different. You can see that this schematic has a red line that dramatically deviates off from this. This is a slide derived from Mitchell's article in Circulation, showing that those individuals from the Framingham Heart Study in the highest quartile, the fourth quartile for pulse wave velocity, indicated a higher likelihood of a first cardiovascular event by 48% when controlling for conventional risk factors. That's huge. After you control for conventional risk factors like smoking, total HDL cholesterol, age, sex, systolic blood pressure, use of antihypertensive therapy, aortic pulse wave velocity, our measure that we just talked about regarding arteriosclerosis, is independently associated with the first cardiovascular event. It matters. This value matters. Now, in the context of obesity, the research is coming out more and more, and it's showing this relationship. Now, while this is not a causal relationship, it is an associative one. And what it shows is with an increase in body mass, irrespective of age, you will have a greater pulse wave velocity. This highlights the fact that maybe obesity is speeding up arteriosclerosis via inflammation and pro-inflammatory cytokine expression. So excessive body mass promotes arteriosclerosis, and you can see this positive linear relationship independent of age. The larger you are, the stiffer your arteries. What's the role in food in all this? I see a lot of people eating a lot of different things all the time. Some of it is questioned. What's the role of food in obesity? As exercise scientists, we focus on one side of the equation. We're thinking constantly about burning more calories. You got to exercise more. Let's stay physically fit. But what about what we put into our body? The food. Does nutrition act as a link between obesity and cardiovascular disease? Does nutrition act as a link between lean and obesity? Is obesity even caused by what we eat? Is it just the fact that we live sedentary lifestyles? But if we moved more, we ate the same stuff that we ate now, would we be the same size? This is the classic energy balance equation. You got food coming in. This is an oversimplification of what happens, but I think it shows an important relationship between energy flow in the system. You got to eat less, they say. This is a way to address obesity, which will address arteriosclerosis by reducing calorie content in foods and promoting that lean adipose tissue. People say what you eat, the carbs and proteins and fats coming into the system, if you want to maintain your body weight, should approximately equal how many calories you expend on a day-to-day basis, with the vast majority of those calories coming from metabolic demands. The next largest portion is physical activity, and a very small portion related to the thermic effect of feeding. I think, in my humble opinion, the research focuses too much on fat. Reduced fat, low fat, no fat. Why has fat been given the culprit logo? I think we ought to adjust our thinking and look at the carbohydrate. Refined carbohydrate consumption in this country over the last 100 years has increased dramatically. We eat refined processed foods more than we eat complex whole grain carbohydrates. So then what do? We reduce the calorie content through the carbohydrate to address obesity. But you look at the artificial sweeteners, and they're in products that you wouldn't even suspect. They're everywhere. And it's kind of mind-boggling looking at those products. What do you choose? What's healthy? Is this going to cause cancer? Does this taste good? Sweet and low tastes like metal to me. Well, the whole point of the carbohydrate manipulation is to still provide sweet sensory characteristics, but reduce the number of calories. So I want it to taste sweet, but I don't want it to give me any extra calories. And if I do this, I can drink diet sodas, I can have these artificially sweetened substances which will preserve calories, and that's the thinking. The USDA has approved the use of several different types of artificial sweeteners, including aspartame, acesulfame K, neotame, saccharin, sucralose, cyclamate, allatame, going by many of the brands that you're familiar with, the Sweet Lows, the Splendas, that sort of deal. Now, I'm not going to talk about why I think these are bad or why I think these are good. I'm just setting this up for the next one, which is this. This is the answer, folks. This is the present, and this is the future. This is a plant that's indigenous to Paraguay and Brazil. It's a plant species in the sunflower family. It's called Stevia, rebaudiana, Berrones. And there are glycosides, functional molecules that have carbohydrate moieties covalently attached to them, that provide very sweet characteristics. For instance, Reb A, 250 times sweeter than table sugar, or sucrose. Stevioside, which is the predominant glycoside in this plant, 150 times sweeter than the taste of sugar. Intensely sweet characteristics. The chemistry of it looks like this. As typical with a glycoside, you have carbohydrate molecules attached to a central structure. This is known as the aglycone. You see 1, 2, 3 glucose molecules. These 3 glucose molecules will be substrate for our microbiota in our gut. We won't use these carbohydrates. These will be used by the bacteria in our gut. Particularly it bonds at the carbon 13 and the carbon 19 is where the bacteria will split this. When that happens, this functional molecule called the aglycone will be released. This is what gets absorbed or excreted in our digestive system, steviol. It's a central structure, eliminated the carbohydrate moieties. This is a functional molecule that has a lot of potential as a therapy in obesity. How do you get the glycosides from the plant itself? This was a study that was done just recently, and it extracted glycosides. The 2 predominant glycosides in the plant are stevioside and Reb A, which constitute approximately 14% of the entire plant mass. There are dozens of other glycosides. Some of them differ by a substitution of a glucose for a rhamnose, for instance. So there are a lot of different glycosides inside the plant. Using HPLC, this method involved temperature at 100 degrees for 30 minutes. And through high pressure liquid chromatography, involving solvents, pressurized pumps, columns, we can adsorb glycosides on resin and then extract this out. Extraction time for stevioside peaks at 20 minutes, 30 minutes for Reb A. The researchers conclude 30 minutes would be ideal for extraction of the glycosides. When you taste this, and if you've never had this, I would recommend that you try this substance, stevia. It's going to fit right here in the type 1 member 3 taste receptors. These 3 carbohydrate molecules are going to interact with receptors and provide an intensely sweet characteristic without calories, so 0 calories. It's natural, really is natural, and it doesn't increase blood sugar. So there was no glycemic response by taking stevia in as a sweetener. Again, this central molecule that will be responsible for the bitter taste in stevia is the aglycone, and it's going to interact with different taste receptors. So it's a heavy molecule, stevioside, that sits nicely in this taste receptor, and via the 9th cranial nerve, afferent signals will go to the brain and say, wow, that's really sweet. But when this structure goes to the gut, you won't absorb the carbohydrates will be split off by bacteria, saving calories. This molecule will help also when it gets absorbed into the bloodstream with natriuresis as well as diuresis. It's going to promote the removal of body water as a result of conjugating steviol to steviol glucuronide. This is going to help bring out water, so it's going to help lower our blood volume. Okay, practical applications of the molecule itself. When you make black tea, no sweetener, black tea. You just make black tea, right? Microwave some water, put some black tea in there, 10 minutes later, black tea. If you sweeten black tea with sugar, if you sweeten black tea with honey, you are statistically significantly reducing the antioxidant capabilities of the black tea. There's an interaction between the molecules. Sugar and honey in plain black tea reduced antioxidant status of the tea, in contrast to Stevia rebaudiana, which preserves black tea antioxidant status. This is an important point for increasing nutrition in our day-to-day lives. Stevia does not decrease antioxidant status in plain tea, or does it decrease antioxidant status in milk fortified tea. Stevia preserves the antioxidant capabilities according to an in vitro assay, DPPH activities, radical scavenging assay. And I think it's an interesting takeaway. I'm just trying to incorporate different use of this plant other than obesity, arteriosclerosis. Just give you something to think about as you sweeten up your foods and that sort of thing. And you're going to be influencing the nutrition in a way that you may not have been aware. Okay, what do we talk about? So obesity increases inflammation. Inflammation promotes cardiovascular risk. My cardiovascular disease of choice for today's lecture has been arteriosclerosis. We look at the energy balance equation, adjusting calories in, adjusting calories out to address this obesity, particularly modified carbohydrate. As a way to modify the carbohydrate, we've incorporated Stevia rebaudiana as a non-calorie promoting, intensely sweet, natural sugar alternative. We look at its chemistry and so forth. Now I'm going to ask a different question. What is the role of Stevia rebaudiana as a mediator of arteriosclerosis and obesity? Is there even a relationship between this functional molecule, vascular stiffening, and increased adipocyte swelling? This is a model that I've put together that I think would summarize my thesis up to this point. This is a working model of inflammation-driven arteriosclerosis in diet-induced obesity. And what I'm suggesting is that Stevia rebaudiana potentially can act as an anti-inflammatory agent in arteriosclerosis. So I'm saying eat the food that you want to eat, be as sedentary as you want to be, keep everything else the way you want to do it. Add in stevia regularly, and this may provide therapy to your body. And how it would do that would be to inhibit this process here. If this is a potent anti-inflammatory molecule, if this molecule does interact with adipokine signaling, and we can decrease inflammation, even if we are obese, will we be able to reduce arteriosclerosis? This is the only paper that's been done on the subject, and it involved mice. What they did was ask the central question, which is, does stevioside, which is the principal glycoside of the plant, downregulate adipose tissue inflammation? Took 40 mice, they randomized them to 4 groups. 2 with normal diets, 2 with high-fat diets. High-fat at 49% total calories is fat. Of the normal, of the high-fat, 1 group was given stevioside, and neither group. So 4 groups, 10 mice in each group. They followed these diets for 3 months. After 3 months, for the last month of this protocol, treatment was given, either stevioside or vehicle, dissolved in a 0.9% sodium chloride solution and given via oral gavage twice daily at 10 milligrams per kilogram per day. So they were hit twice with a dose of stevioside for a month. Mice who were fed high-fat diet. What they show? When you look at the pro-inflammatory adipokines that were increased in the high-fat fed mouse group, you can see here, 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 here. All these are pro-inflammatory adipokines. You can see that the normal mice have significantly lower amounts of inflammation than the mice who were fed the high-fat diet. Diet-induced obesity drives inflammation. Yet, there's a preservation, a restoration, a reversal of the high-fat diet mice who were also given stevioside. Again, suggesting that there's an anti-inflammatory acting mechanism reducing inflammation in the adipose tissue. This was restored. and all the adipocytes all the adipokines that were measured. Stevioside reduces macrophage infiltration into the adipose tissue. You have different macrophage markers as well as marker for infiltration. I'm not a big fan of this staining slide. I put it up here because it looks pretty. There is a difference you can see between the high-fat stevioside column and the high-fat. Just without even knowing what this means, just looking at there's less color here than here. So when you quantitate it, and this is, I prefer this one over here, there is a significant reversal difference in macrophage infiltration according to these markers of macrophage and the chemotactic factor. So even if you induce obesity in a high-fat mouse, you can reduce macrophage infiltration as a result of 1 month of supplementation of stevioside. This is a blot showing decreased expression of phosphorylated IKK beta and IKB alpha here and here relative to this and this, showing that stevioside suppresses NF-kappa B signaling. And if I can downregulate that pathway and prevent the activation of this gene, well, then this is going to be important for downregulating adipocyte inflammation. And stevioside preserves this, even if you are obese, even if you induce the phenotype of M1 macrophage dominance. Conclusions that I have: Stevia rebaudiana extract is a nutraceutical that will help combat obesity and excessive weight gain. More research is needed to support Stevia rebaudiana as a modulator of inflammation-driven arteriosclerosis in diet-induced obesity. There's only that one paper that I showed you. That was the only paper that was done. There's some in vitro work done in individual cell lines, but this is the only thing done in vivo. I have interest in this. A couple other things that I want to show. So that's my presentation. Let me just leave you with this. And I do this because I think it's helpful. You see stevia in the workplace, etc. You see these different brands. This is the worst of the brands, in my opinion. This is cut with maltodextrin, which is derived from corn, which promotes the glycemic response in cavities. So they cut their product with a corn derivative. That's the least desirable stevia product. Truvia is better than stevia in the raw. Truvia has stevia extract and it uses a sugar alcohol, erythritol. Some people have problems with sugar alcohols causing GI complications. But the gold standard is in stevia extract if you want to buy it commercially. And you can even make it yourself, so you can buy the plant and extract the glycosides yourself and store it. And it's a natural way to be closer to the process of giving your body nutrients from cultivating food yourself. Sweet leaf is a standard in stevia products. They cut their product with inulin, which is a polysaccharide that's a natural occurring fiber. So fiber, sugar alcohol, corn derivative. You want to go with this one. Sweet leaf is the brand. If I recommend a brand, it'd be that brand. There's a relation between, this is in humans, this has been done in human beings. You can decrease mean arterial blood pressure. You can decrease mean arterial blood pressure with stevioside. It's incredible. You can decrease blood pressure with stevioside. I told you that stevioside will be conjugated to steviol glucuronide. That's going to help act as diuretic, as a natriuretic, which is going to decrease extracellular fluid volume, which will collectively reduce mean arterial blood pressure. In addition, calcium influx in vascular smooth muscle is inhibited with stevioside, which is going to promote vasodilation, which is going to therefore decrease total peripheral resistance and will decrease blood pressure via that mechanism. It's a nutraceutical, it's a functional molecule, it's here now, and I think it's a great thing. I appreciate your time.
Given the potency that you talked about of it, not using it as a substitute but as a therapeutic agent, is it known what levels you need to have? I mean,
Yeah.
is it like too sweet to be considered?
It's a good question.
Like what levels do you have to have intake
Yeah.
in order to have a therapeutic effect or a preventative effect?
Yeah, that's a tough question. To answer it immediately, I don't know. and to answer it longly, I don't know. So that, they're still working on the dosage, dose-response relationship. How much should you take in? How frequently should you take this in? Once a day, is it better than 3 times a day? Those questions are to be answered. I couldn't give you insight into dosing because there is no insight into dosing at this stage of the game.
The people that have, this came up because my father's doctor was recommending that to him, but he's also on a lot of different cardiac meds.
Yeah, the interaction.
The interaction with that, particularly because it does have a diuretic effect.
Yeah.
You know, does it have to be balanced then with medications?
I don't know the medical interactions. I do not know the relationship between the glycosides derived from this plant and any interactions with medicine and uptake, absorption, or effect. I don't know that relationship, if a relationship even exists. These are phenomenal questions, and it's something I'll look into, but at this current time, I don't know the answers to those. Chris?
Do you feel that the real enemy here is caloric intake instead of a specific macronutrient, because you kind of focused in on carbohydrates?
Yeah.
Do you feel that as far as in a grand scale, is it the caloric intake leading to obesity that's causing the inflammatory effect, or are you trying to isolate carbohydrates as the main enemy, which is what a lot of people are trying to focus in on in this obesity epidemic?
Yeah, that's a thought-provoking question. Those are questions that really tickle my soul. I think the refined carbohydrate is a big culprit in obesity. So while the total energy balance of all the macronutrients day to day is too high, I think what's driving that is the refined carbohydrate. Crackers, chips, pastries, cupcakes. It doesn't promote, those carbohydrates don't promote satiety, so you don't feel full, and you want to keep eating those. This is going to decrease insulin sensitivity, increase basal resting glucose levels, and it's through the carbohydrate. I think fat is more easily tolerated in the body versus the carbohydrate, and it's predominantly through insulin that the effect is having. It's cardiometabolic detriment. So I think to answer your question, the carbohydrate more than the total. If I had to pick one or the other, I think that carbohydrate in this country, the refined carbohydrate, is a major problem, and that's what's driving most of this.
Just from an insulin response standpoint, the fact that people feel the need to eat more, or specifically,
So
my
yeah,
question is, like, if I gave you Pop-Tarts, for example, I'm a big Pop-Tart fan. You know, if I gave you 50 grams worth of carbohydrates in Pop-Tarts versus 50 grams worth of carbohydrates in broccoli,
Right.
taking away or taking anything from an insulin response, if we look at the end of the day and you come up with the same amount of nutritional value from Pop-Tarts or broccoli, from an energy balance standpoint, you know, that's just my only problem with trying to isolate carbohydrates as a bad guy, because everything at the end of the day, from a metabolic pathway standpoint, is broken down into the same component.
But the process, by the time it takes to take 50 grams of Pop-Tarts or 50 grams of broccoli and cauliflower, starting to the finished product, you will expend more energy in the complex carbohydrate breakdown.
It's the thermic effect of food, but from
Right,
a,
so
how,
there's that
what is the
aspect.
percentage of the thermic effect of food from?
So it's a small, so that effect is a small contribution. The total energy requirement to reduce the acceleration of heat production as a result of macronutrient breakdown. So maybe it's more through the insulin pathway, where insulin sensitivity is blunted. The adipocyte will start secreting fatty acids into the bloodstream, promoting atherogenesis. These are interesting conversation points. I love this stuff, but I'm just speculating. That's what came out. Nick?
Yeah, the study you showed, they induced obesity through fat intake. If you could redo this study, would you try to induce obesity through carbohydrate intake?
You got it. I actually talked to Dr. Fleener about this last week. Said there's some research, stevia site interacts with high-fat feeding. What if we induce obesity via high sucrose feeding, leave the fat constant, increase carbohydrate, and see what happens? 100% thought about that last week, actually. Yeah, and back here.
So stevia comes in like a liquid form, and you can use a dropper and put it on your food. Would you say that is better than the granular form that you can buy commercially, or vice versa?
So the liquid form I actually use, I prefer the liquid form myself. It depends on the brand. If we're talking sweet leaf, it's going to be the same. It really depends with the other substances that I named, maltodextrin, erythritol. So if you're a consumer and you're looking, well, which stevia product should I buy? Look at the ingredients and make sure that you trace the source of each one of those ingredients, and you'll see that sweet leaf comes out on top, either the powder or the liquid.
What about side effects? You know, it obviously hasn't been approved very long. If you look at the literature and, you know, you showed that it's, I mean, it sounds like the miracle product, but are there any side effects that one would want to avoid or any?
So there could be a GI relationship. The functional molecule stevia in the gut could bring more water into the lumen, so it maybe will promote diarrhea. So if you have a sensitive stomach, there's a possible relationship. You could have GI issues related to the stevia. So that's the only thing I can think of or know of at this time, GI related.
I saw some posters at ACSM a couple years ago, looking at artificial sweeteners, influence on carbohydrate transporters in the gut. And they were showing that just taking in artificial sweeteners actually increase carbohydrate transporters in the gut, so that you actually, when you take in carbohydrate, you actually take in more carbohydrate because you can. You know, does stevia have any?
And that's a valid question. The transporter that stevia uses in the gut is a monocarboxylic transporter, and which is how it gets into the lumen of the bloodstream. And you're asking basically, does stevia interact with the transporter promoting an influx of carbohydrate?
That just somehow the artificial sweeteners were stimulating production more transport.
Yeah, that's an interesting question. I haven't seen anything of that sort. So I'm not familiar with it, but that's not to say that there's research that isn't there. But I'm not familiar with that particular one.
Will the mice just eat it? I mean, you said they gavaged them, right?
Oh, yeah, they
in that
did.
study. How does that dose level compare to what you would do in a human?
It's a
Is it a
phenomenal question.
a super high dose level? or-
They didn't comment on the relative difference between 10 milligrams per kilogram in a mouse. What would the equivalent be to human beings? They didn't mention in the paper if it's what you would see day to day or if it's higher or lower. So I have to look into that to see how that scales up from the rodent to the human, because I don't know that either.
I have some thoughts to back up your question about the Pop-Tarts and the broccoli. There's been a lot of in vitro studies that has been done that hyperglycemia increases oxidative stress. So when you compare the Pop-Tarts and the broccolis, however, the Pop-Tarts will not induce such a glycemic response compared to the broccoli. But as a healthy subject, I will produce increased amount of insulin to combat the hyperglycemia. But I think it's like a vicious cycle that there is a time there is a hyperglycemia that causes oxidative stress, and the oxidative stress there is evidence that oxidative stress causes insulin resistance. So it's kind of vicious cycle that you start producing more and more insulin resistance and producing more oxidative stress, and thereby arteriosclerosis.
Right.
Whereas the broccoli doesn't. Even though it's the same amount of carbohydrates, but the glycemic response from the broccoli is not as peak as the Pop-Tart would.
Right. Specifically, and when I talk about Pop-Tarts, it's mainly from a post-exercise where you want a hyperglycemic effect, you want that insulin response. It just goes to show, I'm just saying, like, you don't eat Pop-Tarts all day, so I'm not a big fan of using Pop-Tarts on Pop-Tarts or Pop-Tarts, but there's definitely a specific time when those type of macronutrients are going to be more beneficial from a recovery standpoint, building standpoint. And even in endurance athletes, the pastas, the things that have high glycemic index, from a glycogen standpoint, you need that hyperglycemic effect to restore the glycogen processes that you're not going to specifically get through a lot of the broccolis and the low glycemic. But I get what you're saying about the oxidative stress. There's always protein products, but in healthy subjects, people that are regularly exercising, where they keep their insulin sensitivity regular, and then in an obese population, that definitely changes. But I'm just saying, the biggest enemy, I think, in an American culture is the one that we are non-active and that we don't control our diet, and there's a self-control aspect, which high glycemic carbohydrates are gonna affect insulin curve, you're gonna get hungry pretty quickly with that. But at the end of the day, if the energy balance is the same, you can't promote obesity if you're either balanced or at a negative caloric deficit. So that's what I'm getting with the problems with trying to isolate carbohydrates as an enemy versus just total caloric intake.
I appreciate it.